Remember that one of the reasons we were interested in slopes of tangent lines was because we could interpret, for any function, we could interpret its instantaneous rate of change as the slope of a tangent line. So now that we have recognized that the derivative, or we've named the derivative for this slope of a tangent line, we can actually calculate any instantaneous rate of change just by calculating the corresponding derivative. This is really the reason that derivatives are important. It's because they tell you instantaneous rates of change. For example, suppose we have an object that's moving back and forth along a line so that its position after t seconds is given by this formula. P of t is t squared minus 3t plus 1. This is, say, in meters to the right of some landmark, right? So we have our object. This is position 0. Here's position 1, position 2, position minus 1, and so on. And our object is sliding back and forth along this ruler, I guess. So let's find the instantaneous velocity of the object after 2 seconds. Well, instantaneous velocity is just the limit as our change in time goes to 0 of the change in position over the change in time. Right? This is what this is how we interpreted the idea of instantaneous velocity. But this is exactly the derivative of our position function. So we want the derivative after 2 seconds. So we want p prime of 2. So you can see that because we wanted an instantaneous rate of change, we end up calculating a derivative. So this is the limit as h goes to 0. We could use this original quotient here, but let's rephrase things in terms of our usual notation with h. So we need p of 2 plus h minus p of 2 over h. So let me slide this over here to get as much room as I can. So limit as h goes to 0 of, let's see, p of 2 plus h is going to be 2 plus h squared minus 3 times 2 plus h plus 1 minus p of 2, and p of 2 is going to be 2 squared minus 3 times 2 plus 1 all over h. Now we need to multiply everything out in the numerator to see if we can extract a common factor of h so that we can simplify the h in the denominator. So we're going to get, let's see, squaring this stuff, we get 4 plus 4h plus h squared minus 6 minus 3h plus 1. So that's all these first 3 terms. And then for the last 3 terms, let's distribute the minus sign. So minus 4 plus 6 minus 1. Now we can start simplifying things. So here's a minus 4 and a plus 4. There's a minus 6 and a plus 6. And there's a plus 1 and a minus 1. All right. So this is the limit as h goes to 0. So the only terms left are 4h minus 3h. So that gives us h. And then plus h squared all over h. And now we can simplify away a factor of h. By the way, it's a tempting algebra mistake to just cross those out and say the result is h squared, but that's not right. If you're going to simplify a common factor, you have to factor that out first. So h times 1 plus h over h. And now we can cancel the common factor of h. So limit as h goes to 0 of 1 plus h, but 1 plus h is a polynomial in h, so that's continuous. We can just plug in the 0. So we get 1. 1 what? Well, remember, an instantaneous rate of change, our position is being measured in meters, and our time is being measured in seconds, so the instantaneous rate of change, the units is just the quotient of those. So this is 1 meter per second. And you can tell that, you can see this is a unit for velocity, so we did actually compute an instantaneous velocity here. For another example, let's talk about an object cooling sitting on a bench. So suppose we have a hot object sitting in a cool room, and it starts to cool down so that its temperature after t minutes is given by this formula in degrees Celsius. How rapidly is the object cooling after 5 minutes? Well, this phrase, how rapidly, this is really telling us that we're asking for an instantaneous rate of change. And since we're looking for an instantaneous rate of change, that means we should calculate a derivative. So we want the instantaneous rate of change after 5 minutes, so what we should calculate is f prime of 5. And the units that we get will be units for f divided by units for time. So we'll get degrees Celsius per minute. And that is a rate of cooling, so everything is fitting together. Just a note, this function, it sort of works in that it produces a graph like this, where the temperature comes down, but real objects don't actually cool this in this particular way, so that this example isn't realistic. I have a reason for choosing this function rather than the realistic function, but let's just go with it for now. Okay, so we're calculating the derivative of this at 5, so 5 is playing the role of a here, so this is the limit as h goes to 0 of 10. So what we're plugging in for t is 5 plus h. So 10 times 5 plus h plus 32 over 5 plus h plus 3 minus, and now we need f of 5, right? So that's, let's see, 5 times 10 is 50 plus 32 is 82 over 8, all over h. All right, well, this looks like a bit of a mess, but just given the general form of things, because we have rational stuff in the numerator, it seems like we should somehow clear the denominators here. So first, let's do this arithmetic. So we're going to get 50 plus 32, so 82 again, plus 10h, and then in the denominator 8 plus h minus 82 over 8 all over h. So let's multiply the numerator and denominator by 8 plus h times 8. And then same thing here, 8 plus h times 8. All right, so this is limit as h goes to 0. Now we need to distribute here. When we distribute to the first term, the 8 plus h cancels, and we're left with 82 plus 10h times 8 minus, and then when we distribute to the second term here, the 8 cancels, and we get 82 times 8 plus h all over h times 8 plus h times 8. Okay, so limit as h goes to 0 of, let's see, I guess we're going to have to multiply all this out. So 8 times 82, I think I can get away with not working that out, plus 80h minus 82 times 8 minus 82 times h, all over h times 8 plus h times 8. Now in the numerator, yeah, this 8 times 82 cancels, so I don't have to work that out. And we're left with limit as h goes to 0 of, let's see, 80 plus 80h minus 82h, that's minus 2h over h times 8 plus h times 8. And now we can simplify our h's. So we get limit as h goes to 0 of minus 2 over 8 plus h times 8. This resulting function here is rational, and it is defined at h equals 0, so it's continuous at h equals 0, so we can just plug in our 0 now. So we get minus 2 over 8 times 8. We can get rid of a factor of 2 here. we get minus 1 over 8 times 4, 32. Yeah, 32. So minus 1 over 32. And remember, this was degrees Celsius per minute. So after 5 minutes, this object is cooling down. It's cooling because the rate is negative. So that means that the temperature is going down and not up. So, right, always in a rate, the sign is going to tell you which direction the quantity is moving. So this one's negative, so the temperature is going down, so it's cooling, at a rate of 1 over 32 degrees Celsius per minute. Or 1 degree Celsius per 32 minutes, I guess, but it's an instantaneous rate.